All right, chapter 10.3, learning and understanding the universe. Some of the stuff might be redundant, and redundant means that we have already gone through it. I need to chat so I can answer you guys' weird questions. I'm gonna say, ooh, no, God, please, no, no. Can I just put universe? Yeah, sounds good to me. Sounds good to me. All this is a really cool picture because like all of these things are galaxies, which is really cool. And each of those galaxies have billions of stars in them. I think that's really cool. All right. Top. Chapter 10.3, Essential Tasks. By the end of this lesson, you should be able to understand the vast amounts of galaxies and stars and the space between them. Explain the different shapes of galaxies. Identify how technology helps us study space. And number 4, compare characteristics of the electromagnetic spectrum. My dad showed me this picture. It was a bunch of stars and using them. That's really cool. There are billions and billions and billions and billions. Nothing I like more than space. Good thing we have so much space in between us, right, Cole? All right. You can pick anyone you want. That's the beautiful thing. All right, so today we're going to learn about how we learn about the universe. One of the biggest ways we are able to study the universe, all the stars, the galaxies, everything, is that most things, except for something called dark matter, give off energy, and this energy is known as electromagnetic radiation, all right, that travel in the form of waves. Remember, we learned back in the heat chapter that there's a couple forms of heat. One of them is radiation. So radiation is sort of like a wave that goes through space. That's the biggest way we learn about it. I got a bug bite too. Space is through viewing electromagnetic radiation. Space is a hard vacuum, meaning it is a void containing very little matter. Stop copying and pasting, Cole. So, Elena, oh, you're famous. You'll be in this video forever. Electromagnetic radiation is the biggest way we are able to study space. Now, electromagnetic radiation comes in many forms that we can't see, but we can see some of it, all right? And that what brings us to, oh wait, a video. Okay, never mind, sorry. Let's see, hopefully is my volume on the right thing here? Let me just check real quick. Yeah, that's good enough. All right. Very small. We'll go through that in a second. Wait, you guys can't hear that, can you? Here, let me put it louder. Change the volume source. Give me a little momento. Okay. It should be better.
Chicken mushroom. Dear Tim and Moby, what is the electromagnetic spectrum? The electromagnetic spectrum is just the name for a bunch of types of radiation organized by the amounts of energy they carry. No, it doesn't have to be from radioactive material like plutonium necessarily. Radiation is any movement of energy through space. You can think of this radiation as a wave made up of moving electrical and magnetic fields. You can think of it as a stream of particles called photons. EM radiation is kind of indecisive. Sometimes it behaves like a wave, sometimes like particles.
You won't have to know that part.
Starting with the lowest energy level, The 7 types of EM radiation are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays.
I'm gonna stop right there. He's gonna talk about it, but like Cole, when that percentage, all of that is electromagnetic radiation. The only ones that we can see is visible light. So all that other stuff we can't see. And we're gonna go over the rest of it after the video. If I can play it.
Radio waves are used to transmit radio and television signals. AM radio uses low energy waves, FM radio uses medium energy waves, and TV uses high energy waves. Cell phones use radio waves too, and stars in space can also emit radio waves. Microwaves are used in microwave ovens.
And we'll also talk about it in a second. I don't know if you ever heard anyone say that, like, oh, they're putting up these 5G towers and it's gonna cause cancer to everyone. Radio waves are very, 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 very safe. They don't do anything to anyone. So when you hear someone say, oh, this cell phone tower is gonna cause cancer, don't call them stupid, but teach them about the waves. Now, on the other side, so radio waves are like very safe. On the opposite end, the gamma rays, the higher the frequency of the wave and the electromagnetic spectrum, the more dangerous it is. So gamma rays, very bad. Gamma rays are very bad. You get hit by a gamma ray, you're probably gonna die really quickly. Luckily, we'll talk about it. I think they're gonna talk about it here. Our atmosphere blocks most of it, but radio waves are very safe. So no, cell phone tower does not equal cancer. So if someone does say that, say, you need to go back to 6th grade science.
Systems. In the oven, microwaves heat up the water molecules in your food.
So microwaves is a form of electromagnetic radiation.
And sent back to the radar system to pinpoint
So is radar.
the exact location of the plane. Infrared rays are often produced when an object radiates heat. You can't see them, but you do feel them. A remote control uses infrared rays to send signals to your TV set, stereo, or DVD player. Infrared radiation can also be used to take special photographs called thermographs. The next type of radiation in the spectrum is visible light. Thanks to special cells called cones, our eyes can perceive wavelengths of visible light as color. In order from lowest to highest energy, the colors are known as red, orange, yellow, green,
You'll see in a second,
blue,
Elena.
indigo, and violet. Ultraviolet rays occur naturally in sunlight. Fortunately, the ozone layer blocks most UV radiation from reaching the surface of the Earth. In large doses, UV rays can cause skin cancer and cataracts. X-rays have a very high penetrating power. That means they can travel easily through just about anything. Doctors use small doses of them to make pictures of your bones and organs and stuff. The X-rays travel more easily through flesh than bone, and that's why shining X-rays through someone on a sensitive film can make an image of your insides. Gamma rays are the most energetic waves in the EM spectrum.
Gamma rays.
Most gamma rays coming from space are absorbed by our atmosphere. But gamma rays are also produced on Earth in high-energy reactions, such as nuclear explosions. Gamma rays do a lot of damage when they pass through living cells. Where does the radiation come from? Well, all matter is made up of atoms, and each atom is made up of protons.
You guys don't need to know this part.
Electrons orbit around the proton and neutron nucleus at different levels, or shells, depending on how much energy they have. Sometimes an electron drops from one energy level to another, giving off energy of varying strengths. All electromagnetic radiation moves through the universe at a constant speed of 300,000 kilometers per second.
Pretty fast.
EM radiation can
Speed
even
of light.
travel through the empty vacuum of outer space. The higher the energy of the wave, the more stuff it tends to pass through. Oh, my suit's cold. Thanks. I was kind of afraid you were going to nuke it. No, I meant literally.
All right, so here's something that might help. So once again, the spectrum is like all of the electromagnetic radiation, all right, from one end to another. It's a giant like spectrum, sort of. So let's see if there's anything I want to say from the writing. It's basically any energy that travels and spreads out in the form of waves. They can come from anything, the lamp, a TV remote, the sun, radar, radio, all that stuff is radiation, electromagnetic. So, like I said, there's like a spectrum. So on one end, up here, let's see, where's my little thingy bobber? The one end up here, you can see that these waves are very long. Down here, it's very short, like ba-da-da-da-da-da, all right? The longer the wave, the safer it is. The further the distance it travels, the less it penetrates things. Radio waves are the longest, all right? Then they get shorter in microwaves, then infrared. How many of you have ever seen an infrared picture before? Also known as a thermal picture, where they take a picture and you can see the different temperature of things. Military people use it in their scope so they can see people in the night. Then there's the visible light. That's the stuff we can see, like red, yellow, green, blue, purple. And then ultraviolet light, you know UV light, that's the stuff that can give you tans and skin cancer. And then the further you go down, or the more high frequency it gets, the more dangerous it is. So more dangerous. Ultraviolet, we know, can hurt us. X-rays can be very dangerous. That's why they only use it very briefly when they take an X-ray of you. That's why they put these, a lot of times they'll put things to protect you, like if you're wearing like a lead vest. And that's why the doctor stands in the other room when they take the picture. They don't take it in there with you. And then gamma rays, that's the most dangerous, the highest frequency, the highest energy. So when, the sun, what we talked about in the last chapter, goes through nuclear fusion, it creates electromagnetic radiation. It makes all of these. All of these are made by the sun's light. But just a lot of them, like the gamma rays and the X-rays and the UV rays, are all blocked by our atmosphere, so it keeps us safe. Did I answer your question about the gamma ray, or you still need that, Elena? It's just a frequency of a radiation that's super fast, and it penetrates things, and it's very dangerous. It can it gets into like your cells and destroys your cells and breaks them down. Try to think of it like, it's obviously invisible. All of these are invisible to us except right here, the visible light. So out of all of this light, only this small portion is stuff that we can see. Just everything I just talked about is a form of energy in the form of a wave. A gamma wave is just something that goes up. The frequency is so high and has so much energy, it can just destroy things by touching it. I don't think gamma ray itself, I didn't want you guys to know too much detail. I was trying to give you guys the least amount of information as possible to remember. You might have to know the order from least dangerous to most dangerous for the quiz. But that's pretty much it. I might ask, is there forms of light, or is there forms of radiation that we can't see? You'll obviously say true, because there's a bunch that we can't see. Something like that. In order. It just depends if I say from safest to dangerous, or least energy to most energy. The least energy, you can just look at the wave. The least energy is the radio. Then it gets more and more energy and more dangerous as you go down. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. So on this one over here, it's just to the left. And it says right here, it has shorter wavelength, higher frequency, higher energy. They'll go this way. All right. No, I froze. All right. So from radio to gamma ray, it gets stronger, more frequent. From radio to gamma ray, it gets higher for energy, higher frequency, shorter wavelength, and more dangerous. And another cool thing, I don't think it talks about in here, as far as visible light goes, I'm not sure if it does. When we get light from the sun, I don't think you guys should know that. I'll talk about it at the end if we don't get to it. All right, we gotta keep going. There's like a lot more. All right, so we're just gonna talk about visible light. Obviously, one of the forms of the electromagnetic spectrum is the visible light. Yeah, we can talk about it now. So the cool thing is that in the light from the sun contains all of the colors. You can't see it when it comes down from the sun, but light from the sun contains all of the colors we see: red, orange, yellow, green, blue, violet, all that stuff. Has all of them. When the sunlight hits an object, all right, when light hits an object, it absorbs colors. Whatever color, and this is, I'm not going to put it on the test, whatever color is not absorbed by the sunlight or by the object is what you see. So if I'm wearing a pink shirt, the light from the sun is being absorbed. It absorbs every color except pink. And because pink is not absorbed, that's why the shirt's the color pink. That's why in the grass absorbs purple, it absorbs blue and yellow and red, but guess what? It doesn't absorb green, so that's why grass is green. So whatever color something does not absorb, that's what it is. So that's why in Antarctica, when they say, oh, sunlight reflects because it's white, white means that none of it's being absorbed and it's being all reflected. Black means it's all being absorbed. That's why it gets so hot, because it's all being absorbed. It's just you don't need to know this. It's just sort of like, I think I learned it in, I don't remember what grade. You might learn it in 8th grade about this, but light is really cool. Things are the color they are because of the color they don't absorb, which is neat. Like my hair is brown because my hair absorbed all the colors except brown. So it reflects brown. Whatever color it doesn't absorb, it reflects, which is sort of neat. So this slide, honestly, if you wrote stuff about the last slide, you just have to know you just have to know what visible light is. A visible spectrum is inside the electromagnetic spectrum. It's one of the lights the only light that we can see. That's all. Visible light is the only light we can see. The only radiation waves we can see. And it's a very, very small, it's a very, very small portion of the light. I'm not sure, but I think some animals can see infrared light, like they can see the heat signatures. But most animals and living things cannot see the other forms of stuff. Honestly, it'd be a little crazy if you could see all the radio waves. It'd be sort of scary because there's a lot of them. Yeah, Austin, go ahead. Wait, you're unmuted. Go ahead. I thought you were unmuted. I tried to unmute. There you go.
Well, if you had like a tie-dye shirt, would it be every other color than the tie-dye shirt, or in certain spots?
In certain spots. Yep.
Okay.
Yep.
I knew it was one of those two.
Yeah, I always thought that was sort of interesting about light and color. So this is, I think this is once again redundant since we went over everything, but this is just saying that gamma rays have a the most energy. They're the most dangerous. They have the most frequency, like up and down. They penetrate things. And the radio waves are the opposite. They're long, they're safe, low energy, they travel far distances. That's why we try to like message aliens with radio waves, because they go the farthest. Yeah. All right, that's pretty much it. You just have to sort of know the spectrum. You have to know, I'd like for you to know the order. I'd like for you to know that the further you go towards gamma ray, it's more dangerous. Did I do it right? No, wrong. All right, let's see. Okay, now we're gonna learn a little bit about telescopes. So basically, electromagnetic spectrum is really important for us to study space, but we can't see it. Most of the light we can't see, so we need to develop tools. Aliens, wait, what? They stank? Aliens, what? AKA me, you're a little alien? So we develop telescopes and different types of telescopes to help us see the light that we can't see, the radiation that we can't see.
What is a telescope? Let me see things far away. The moon is about a quarter the size of the Earth. But because it's so far away, it looks pretty small. You can see it because light reflected off of it focuses a small spot of light on your eye's retina. From what you said, it just looks like a little glowing yellowish light spot. With a good enough telescope, you can see much more detail, craters and mountains and stuff. Telescopes capture and magnify light. As you can see in this simple telescope, a large lens in the open collects the light bouncing off of a faraway object and focuses it at a point inside the body of the telescope. Then a smaller lens in the telescope's eyepiece magnifies that focused light and projects it into your eye. Since the light has been magnified, the image takes up much more of your eye's retina and you see more detail. That's a refractor telescope, one that uses glass lenses to gather light. There's another kind, a reflector telescope, which uses a series of curved mirrors to gather and focus light. Light comes through the opening and is reflected by a curved mirror onto a second mirror, which reflects the light into your eye. Some telescopes are better at collecting light than others. The aperture of a telescope is the diameter of the lens or mirror that gathers light.
You don't need to know that part.
And the light magnification is the telescope's ability to enlarge.
I also don't know that part.
Well, no, there are many different types of telescopes. Optical telescopes include the simple handheld ones that pirates use, and binoculars, which are really just two telescopes stuck together so you can see in stereo. There are also giant telescopes like the Keck Observatory in Hawaii, and the Hubble Space Telescope, which operates from Earth orbit, where its images can be free of the distorting effects of Earth's atmosphere. All optical telescopes magnify visible light, so it's stuff you can see with the human eye. But there are other important types of telescopes that see in other kinds of radiation. Radio telescopes see in radio waves. Radio telescopes can be used alone or together with other radio telescopes to study things like stars and other really distant space objects. They're also used to collect data from satellites and space probes. Other telescopes collect things like X-rays, gamma rays, and infrared light, mostly from stuff that you just can't see or visible light. Hey, be careful. Oh.
All right. So basically, there's a couple different types of telescopes, and you don't have to know how to make a telescope. You don't have to know specifically, but I'd like for you to know that there are different types of telescopes. All right. The first type is an optical telescope. Optical telescopes are simply telescopes that help you see visible light. So things that we can normally see with the human eye, they're just too far away. Optical telescopes help you see them. That's all they do. all right? And then there's two types of optical telescopes. There's a refracting telescope and a reflecting telescope. I don't think I'm gonna make you guys know the difference between refracting and reflecting. Honestly, that's like, it seems sort of like pointless for me to test you on. Like, it's not gonna be like you have to know that later in your life. I mean, you might need to know the different types of regular telescopes, but not the different types of optical telescopes. I mean, you've seen these giant ones probably, maybe your dad or your mom or whoever has them. The Hubble telescope is a giant reflecting telescope, the one that gets all those pretty pictures. A regular, like, pirate telescope, refracting one that has two lenses that help you collect light. But basically, optical telescopes just help you see light better further away. That's all. It's better at collecting light than your eye is, so it enhances the picture. Basically, that's all it does. Because your eye is technically, if you want to get really weird, you could say it is a telescope where it has a lens when light comes in it and it presents a picture on the back of your eye, which sends the nerves to the optical nerve and all back into your brain and processes it. If you really want to get it, we're like just like giant computers. Yeah, I can go down a rabbit hole with that, but all right. So there's optical telescopes that help you see visible light, all right? Okay. Then there's the other type of telescopes. Wait, what is this? I must have not, oh, I didn't finish. Oh, I didn't finish. Okay. I don't have the picture. This is from last week. The other type of telescopes that they did mention is like radio telescopes, and different types of infrared and gamma ray telescopes. They have different telescopes that can measure different portions of the electromagnetic spectrum. And here, just so you guys can get the whole thing, I'm gonna go real quick and type in, let's see, radio telescopes. Hopefully something good pops up. Yeah, they're like these giant telescopes. Let's see if I can get a picture that's taken. What do we write? Oh, I guess they don't even have pictures here. How about a gamma ray? There we go. These are what the gamma ray telescope pictures look like. A lot of times they'll come from what we call probes. Okay, so back to your question, Elena. You just have to know that there's optical telescopes, and then there's telescopes for each type of electromagnetic radiation, pretty much. Yeah, pretty much nothing. I'm gonna try to make this test pretty easy. There's a lot of confusing stuff that is not in fact. Like even this part, I'm not gonna make you guys memorize the entire history of space exploration. That'd be sort of mean and cruel, right, Elena? This is just some interesting stuff. So as far as space exploration and probes and just the timeline, they launched fruit flies into space. That was the first thing they ever did. And then the Soviet Union launched a dog into space. And then these two things sort of started the space race. I don't know if you heard of that, where we were sort of like in the Cold War too, competitive with Russia, trying to be the first person to put a person on the moon. That was us. Eventually, in 1969, we were the first to get a. I believe they were first to send they were the first person to send someone into space, though. But we were the first person to land a person on the moon. Some other interesting things is these Voyager probes are really cool because they just sent them out into deep space and they're still going. One of them has like a picture of what humans look like and like some classical music that they're trying to send as a message to aliens whenever they get it. Never. So do we, yeah, music. There's music on it. And the music is supposed to be able to keep playing for billions of years, which is sort of cool. I don't know how they do that, but some more current things. The Hubble Space Telescope is, what is that, 30 years old now? The first rover on Mars is 2003. International Space Station was 1998. That's pretty cool. But yeah, you guys don't need to know or remember any of this. There's a couple space shuttles that did blow up. Does America own the moon? Huh, it's a good question. I would say not anymore because the flag we put down there either isn't there anymore or the sun bleached its color so much that you can't see the American flag. So technically, I would say it's not ours anymore. Yeah. Who's Victor? Who's Victor? All right, we're just gonna keep going. All right, space probes. These things are cool. Space probes, we use space probes a lot because obviously they do not endanger human life unless they fall on you in your home. I think that's actually happened before. They are sent out into space to gather large amounts of information from different planets, the sun, and deep space. So each probe basically goes and a space probe is designed to get information from space. That's pretty much all you need to know. Each probe has a mission to gather information from space and send it back to Earth. Oftentimes probes will have telescopes on them. I'm trying to think of just what I want you to know. There's not a lot I want. I honestly thought about not even giving you guys a section to do notes on this week. I honestly thought just notes are optional. Let's see. I mean, everything we know about the sun, how hot it is, what Jupiter is, that, you know, there's actually boiling water underneath Uranus. Like, we all know that from space probes. Yeah, we send out a lot of space probes, way more than we send out people. This first probe was Sputnik 1. That was, you know, from the Soviet Union. Like I said, that launched the space race. Let's see. Most famous probe is probably Voyager 1. It's the one that travels further in space than any other human-made object. Let's see. February 10th, 2010, it flew past Jupiter and Saturn. I think it's past Pluto now. I think it's way out there. It's really far now. TV dancing on the moon. It's fabric, I think. What? My dad and brother say that the American flag on the moon is not made out of metal, but I do. I have no. Why would it be? How would it be made out of metal? I saw it. It thought it waved, didn't it? Wait, did it wave? I don't think I've ever watched the actual video. Wait. What else is there? Yeah, these probes can do a lot. They don't just take pictures. They don't just say, oh, what's the temperature? They can figure out a lot of different information. And one important thing to know about the probes, you might want to write this down. This is sort of important, is that the reason we can't just use the probes from Earth, and we have to send them out into space, is because our atmosphere and our magnetic field around Earth actually prevents us from getting good information. We actually have to get it out of Earth's atmosphere, out of our magnetic field, to actually get good information or better information. Yeah, tell your brother he's being annoying, Tenny. All right. I'm not going to watch this because this is 10 minutes long, but you guys can go on YouTube and watch this if you want. I think it's approved. Hopefully it's approved. It's like the 7 coolest active space probes and what they're doing right now, which is, I thought that was pretty interesting. I watched the whole thing. They eat space food. I mean, we could play it, but it's 10 minutes long, and I don't want to make this video super long. This one's sort of cool, though. This is, we may play this sort of quick. This is just them launching a space probe into space.
They launched a space probe that will embark on a 7-year mission. This is a live look at the launch site.
This was 4 years ago, I think. They launched a spacecraft with a probe to go to an asteroid, land on the asteroid, get stuff, and then come back.
In the process of forming, they're going to spend an enormous detail. Things besides that going to a black and slightly.
And this is in Cape Canaveral. They launch a lot of stuff.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of Osiris-Rex. Its 7-year mission.
And one of the another facts is the reason why we have to make rockets and have such powerful fuel and thrust is that to get out of Earth's gravity, you have to have a lot of force going against our gravity to exit our gravity. If you took a plane and just tried to take a plane and keep going up and go out, it wouldn't go. Well, I guess technically it wouldn't go because the engines would break, but it would be too cold. Mr. G, I have an actual question. Okay. What is your actual question as this rocket is going? You want to say, wait, you're unmuted. Or I tried to unmute you. Wouldn't the spaceship explode or break going up through the atmosphere? No, it does, like when it goes through that thermosphere, it's very hot, but that's what the ship has on the outside. Remember when I showed you guys I actually took the mini flamethrower to the space shuttle piece and I heated it up and then I waited like 5 seconds and I put my hand on it and it was all cold again. They have special thermal plates on the outside of rocket ships that protect them from, you know, the very hot thermosphere. Sometimes they do blow up though, but usually it's not because of the atmosphere, it's something wrong with their systems. Yeah, I thought that's one of the coolest things. All right, let's just keep going, try to get this over with. Hi, Timmy. You look so happy. All right. From stars to galaxies. So now we're just going to go sort of with the back to the universe stuff. Not as much with how we learn it. So far, we use the electromagnetic radiation, and we study it with different types of telescopes and probes to figure out unique things about the universe. That's pretty much everything right there that we just learned in, half an hour, summed up in one sentence. So we use electromagnetic radiation to figure out the secrets of space, pretty much. All right. So one of the hardest things, let me see what, I just want to make sure what the next slide is. All right. One of the harder things for us to study the galaxy was trying to figure out how far things are away. And I don't know if you ever thought, like, how do they know how far away it is? And for the most part, they use something called a parallax, and we're going to go over that in a second. That's actually something that I want you to know. This image from the Hubble Space Telescope has more than, if you count every little dot, these are all galaxies. There's over 3,000 of them just in this picture. And if I could show you, this picture is just like a little tiny piece of like when you look up in the sky. Like it's not like the whole sky. It's like a little tiny little dot in the sky, which is sort of cool. To figure out what's a type of metal. Yeah. So you guys, I mean, if I ask a question on the test, like how many galaxies are in the sky when you look up, you should just say billions or millions. Like it should not be like, oh, there's like 1,000 up there. No, there's like billions. You should see the picture that my dad showed me. So in this picture, all these galaxies have billions of stars in them. That's why they're lighting up. Wait, what's the picture? Can I see? It's on his iPad. Okay, well maybe later. All right, so a parallax is what astronomers use to figure out the distances to planets and stars that are far away. You can't just like take a ruler and go like, looks like it's that far away. Or I'm just gonna guess. They actually found out a way to be pretty accurate about how far things are away. And this is how they figured out. The video explains it the best. I like this video.
Look at mountains and hills in the distance. If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower. In the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seem to shift position relative to more distant objects like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the sun to the opposite point along its orbit, and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately.
All right, so basically, if you're a little lost, they just they'll take a picture and the Earth is over here at a certain planet or star, and then they'll wait exactly perfectly 6 months till the Earth is on the opposite side, and then take a picture of the exact same object, and they can figure out the angle difference, and then using some special algebra, they can use that angle to figure out how far away it is. So it's actually like mathematical, scientific, it's not them guessing. They use math, guys. They use actual math. Math is useful in science. So basically, a parallax, if you want to write something down, is how scientists figure out how far things are away in angles. That's the simple way of putting it. And they know how to do that. And then they can sort of so if they know the distance of this star, they can estimate, like say a star is behind it, they can figure out how far away the star behind it is based on how fast it's moving, just like how in the beginning they said that the trees move faster than the mountains behind it because they're closer to the road. Sort of like that. I know it's super complicated and confusing, but that's the best I can do for that one, because it is sort of hard. And you're 6th graders, and you shouldn't have to know this, to be honest. But you're advanced 6th graders, so Elena has to know it. Okay, so now we're going back into the actual star stuff and the universe and the galaxies. No more studying it. All right. So there's different types of star systems, Elena. There's basically two big types, all right? Star systems that have two stars are called binary star systems. Binary means two, means there's two stars in like one solar system. So like a planet would see two suns, so to speak. And then there's some solar systems that have more, 3 or more, and those are just called multiple star systems. They can have 3, 4, 15. All right, Sarah, no share. He's not even listening and playing Fortnite. I don't know what this YouTube video is, but you guys can click it. Maybe it's a Rickroll, Timmy. All right, so binary means two. Binary means two. Anything more than that is just called multiple star systems. A lot of times in binary ones, one is either bigger and smaller or brighter or dimmer. That's a lot. That's good. They're usually not the same size as each other. Oftentimes when there's two stars in a system, eventually it does explode. One explodes or one eats the other, and either a nova or a supernova happens. You don't need to know that though. Weirdly enough, there's actually a lot more planets in solar systems with multiple stars. That doesn't mean there's more life, but there's just more planets. I don't know why. All right, next one. So a star cluster. A star cluster is a ginormous grouping of stars. That's all it is. That's all you have to know. A ginormous group of stars is called a star cluster. Right here, this is a star cluster. How does it rotate with multiple suns? Usually one sun has more gravity or one star has more gravity. Usually they're not the same size. And whatever one has more mass and more gravity, the other star spins around it, just like a planet would. A lot of times they will smash into each other, or one is like dying and one is like alive, and one will eat the other and then blow up, and then they make a nebula, and it's all pretty. Oh, yep. So just need to know, star cluster is like tons and tons and tons of stars in a group. Did you fall? Yeah, of course I did. You told me to go look. All right, I'm gonna keep going. Sorry, Lynn. All right, so this you'll have to know. There are 4 different types of galaxies, and the shapes of them. Spiral galaxy, which has a center, like a bulging center, like a circular center. It has like arms that come out almost like a spiral. You'll see it on the next page of the picture. A spiral galaxy is what we have. The Milky Way is a spiral galaxy, which is actually a pretty rare type of galaxy. The most common type of galaxy is number 2, an elliptical galaxy. They're round, they have a lot of gas. They usually only have old stars. Lots of gas between the stars, making them like very, like a thick, like milky looking color. Like there's not, you don't see like the black in between it. It's hard to see through these galaxies. You can sort of see through the Milky Way in between like the arms and stuff, but an elliptical galaxy is more like a ball of light than anything else. And a regular galaxy usually happens when things collide, like galaxies collide with each other sometimes, and They just don't have a shape anymore after they collide. They're sort of just like a disorganized mess of gas and dust. So there's no shape to it, really. And then the last one is a quasar. Quasars are like brand new young galaxies. They're usually fairly big and have a black hole at the middle of them. Most large young galaxies all have black holes at the middle. Oftentimes, the around a black hole will actually like light up in a quasar, which is sort of cool. Tell your brother to stop losing. You can if you want. All right, I'm gonna show you the pictures, Elena. All right, so who can figure it out? Which one's which? Timmy, can you figure it out? Which one's which? All right, we'll start with this. Anyone want to type in what this one is? The answer is spiral. Lana got it right. What about this one, top right? Top right is irregular. Elena got it right again. What about top left? Timmy, you sticking with that answer? All right, let's see what everyone else says. The answer is, it is an elliptical. And then the quasar is this one. The black hole is in the center. You can't see it from this angle, and it actually sort of shoots out light. Elliptical, irregular, spiral, quasar. The spiral is very easy. You can see the spiral. An irregular doesn't have a shape. The only thing that helps you with the elliptical is, like I said, it's sort of like it's hard to see through it. It's like a ball of gas and light. And then the quasar, you can like literally see the energy coming from it. Sort of looks like a spiral too, actually. But all right, those are the four. All right, we're almost done. All right, astronomers define, so you do have to know the universe is defined as space and everything in it. That's the universe. If I ask you what the universe is, you have to know it's space and everything in it, all the matter, all the dark matter, all that stuff. All the things, man. I hear you. You're off mute, so I hear you. All right. Yeah, you got them all right, Elena. 100%. It's robotic. Robotic. All right. So, you don't need to know that. You do have to know, once again, that things in space are so far apart that they have special units to measure it, and that's the light year. When we're measuring outside our solar system, they almost always use light years. So if I ask, like, if we're trying to measure the distance between galaxies, what would I use? Meters, kilometers, and AU, or a light year? You would say light years. Remember, light years is a unit of distance, not time. Timmy has corona. Oh no! Ah! Ah! He's gonna give my computer a virus, man. Another thing that we didn't really work on a lot, but I think you might have done in math class, is that a lot of times astronomers use numbers and distances that are so large that they have to shorten them up. And the way they shorten them up is using scientific notation. That's where they put the number with a decimal and one digit in the tenths place, and then put it times by a power of 10. And that represents a much bigger number. Okay, bug bite lady. All right, another test. It's also known as exponents. What number would this be? 2.5 times 10 to the 5th. Did you guys learn exponents in math or scientific notation? 250 is close. No, it's not. Never mind. Not even close. Nice try. And if you do not know how to do this, I will teach you how to do it in a second. It's actually very, very easy. It's much harder to put it in scientific notation than to undo it from scientific notation. I actually think it was one of the first things I did with my kids last year. The answer, 1, 2, 3, 4, 250,000 is correct. It would be like this. So you do 2.5, and then this is the way I do it. I take 10 to the 5th, so that exponent means I'm going to move my decimal over 5 places to the right, making the number bigger. So 1, 2, 3, 4, 5, and then I just fill in the divots with zeros. So it's 250,000. That's all. All right. If this was a negative number, though, which it does happen, you would go to the left. That's all. Negative exponents make the number smaller, go to the left. Positive exponents make the number bigger, go to the right. What about this one, Elena? Can you do 4.7 to times 10 to the 12? Tim, you can't. He's just sitting there with his nice headphones on. Well, I think Sarah beat you. 1, 2, 3, 4, 5, 6, 7, 11, 12. Sarah wins. Good job, Sarah. Yep, so you do the same thing. You just move it over 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So they do that a lot. Like instead of, writing out that number, they'll say 4.7 times 10 to the, better not use a calculator. All right, we're almost done. We're almost there. We're almost there. Oh, this thing is so cool. All right, I had so much fun with this. You should use it. It's called Scale of the Universe. All right, here we go. This thing is awesome. All right, so I zoomed in all the way. All right, so this is the smallest thing that we have an idea of. And these are theoretical. We do not know these exist. So I'm gonna go out, and further out, and further out, further out. And then this also, a neutrino, we think exists, but we're not sure yet. Okay. And then same thing, I have no idea what that is. I have no idea what these are. As a science teacher, I've had to look that up. I have no idea what those are. All right, so everything smaller than that, we don't know exists. But now, we know about neutrons and protons. All right, where's an electron? All right, electron must be somewhere. Electrons, okay, there's an electron, the nucleus, all right? So those are like atoms, the size of atoms, all right? And they're, whatever, femtometers, they're very small, 10 to the negative 13th power, very tiny. All right, gamma ray. Remember I said gamma rays are very short, very powerful. There's the gamma ray. There's a helium and hydrogen atom, the things that make up the sun and stuff like that. That's how tiny they are, very tiny. You keep going out. Carbon, water. Water molecule looks like Mickey Mouse. All right. There's the X-ray length. Keep going. DNA. That's how small DNA is. Keep going. There's viruses, bacteria viruses. This is the largest virus known to man, the Mimi virus. Viruses are very tiny. Violet light, that's like a light that we can see, is that small. There's our chromosomes that make us like a boy and a girl. X and Y chromosomes. Blood cells. You'll learn about all those next year, the cells and stuff. A dust mite, the thickness of paper. Air, that's pretty cool. And then ants, pencil lead, grain of rice, coffee bean, chicken egg, penny. We'll keep going. We'll keep going. Okay, there's humans. Now we're at human. There's a dodo bird, a basketball. Keep going. That's you, right there. There's a lot. It's cool. They actually have a Minecraft server in this thing too. There's a giraffe, an average house, blue whale, Boeing, tree, football field, pyramid. Keeps getting bigger and bigger and bigger and bigger. I'll just keep going. There's Central Park in New York. See, radio wavelengths are very long. That's how, like an 8, they're very big. Radio, very long. Mount Everest, West Virginia, California. I thought it's cool. Like California is almost as long as Pluto is. I thought that was sort of neat. Earth, USA, Asia, Venus. Keeps going out. Now, oh yeah, there's Minecraft World. I think that was sort of funny. Minecraft World is actually bigger than Earth, apparently. If you like used it as like a real world, I think that was sort of cool. You can keep going. Stars and bigger stars, bigger stars and bigger stars and bigger stars and bigger 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 and bigger. All right. So even the biggest star, which is ginormous, the Kuiper belt is what goes around our solar system. So the edge of our solar system, like our solar system can fit like all of the biggest stars in it easily. So our solar system, remember, is huge. There's the distance from Voyager 1. That's the one with the selfie of humans and then the music playing. That's how far away it is. And there's nebulas. That's a light day. How Tom said that a light year was very far. Light day is just right there. And keep going. Distance to the, well, I don't know what that is. Nebulas, 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 nebulas. There's a light year. And then the Oort cloud. Nebula, 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 nebula. Pretty colors. Nebula, 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 nebula. And then we have our galaxies. Small galaxies, small galaxies, small galaxies, small galaxies. There's the Milky Way. Galaxies, galaxies, galaxies. What is this? This is a cluster of galaxies, cluster of galaxies, cluster of galaxies. Clusters, giant galaxies. And then we're done. If I go into space, can I hear the music? You mean from Voyager? I don't know. But I like doing this. What you do is you just go zoom, 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 zoom. That's fun for me. Still going. And it actually shows you like 10 to the power of actually how big things are too, which is sort of crazy. How high was this girl? All right. Gotta go back. All right. Wait, gotta make music stop. Go away. All right. I think it's really cool. Looks like, yeah, it does. I think that's sort of what they were going for. Hey, that plank can't see me. I don't think you can see it either. Yeah, let's watch this.
Wow, there sure are a lot of stars up there. Okay, speaking of which, dear Tim and Moby, how did the universe get here? Thanks, Iris. Any ideas, Moby? happened at the very beginning of the universe. According to the Big Bang Theory,
Like
the
5
universe
minutes
started
after
around
this?
14 billion years ago. Back then, all the stuff in the universe was packed together in one dense point called a singularity. It's hard to imagine, but
Like
that
5
little
minutes.
ball contained all the elements that would make up the universe as we know it. No one is really sure why, but this singularity exploded, sending not just matter, but space and flying in all directions. Cosmic explosions would be called the Big Bang. It was real hot at first, about 10,000 million degrees. After things cooled down a bit, the first stars and galaxies began to form. All the matter and energy in the universe continued to expand from that initial burst, and it's still expanding to this day. The Big Bang Theory explains why. Okay, all right. Imagine you decide to bake some raisin bread. I don't care if you don't like raisin bread. It's just an example. Anyway, when you put the raisin bread in the oven, the raisins are pretty close together. As the bread cooks, it expands, and the raisins get farther and farther apart. There's really no center to it. Everything's just getting farther and farther away from everything else. You can think of the planets and stars and galaxies as raisins in a really big loaf of raisin bread that is constantly expanding. But no, it's not going to get burnt. It's just an example. Like other scientific theories, the Big Bang Theory is more than just a guess. In science, a theory is an interpretation of how some process works based on lots of hard evidence. Of course, the Big Bang wasn't always so widely accepted. It was first proposed in 1927 by a Belgian priest and astronomer named Georges Lemaitre, who proposed that the universe started in a giant explosion. There have been other theories about how the universe began too. One was called the steady state model, and it said that there didn't necessarily have to be a beginning to the universe. Matter just sort of appeared. But a few years after Lemaitre came out with his theory, American astronomer Edwin Hubble discovered major evidence supporting the Big Bang. His observations suggested that not only is everything in the universe moving away from everything else, but that it's taking the same amount of time to get to where it is today, all starting off from a single position. Later in the 1960s, and especially in the 1990s, several radio telescopes provide even more concrete proof that the Big Bang theory is correct. In fact, one telescope was able to look so far into the distant universe that it actually found leftovers of the radiation given off by the Big Bang. That was awesome. Isn't it amazing how scientists are all discovering things about this universe of ours? I mean, you never know what.
All right. We're almost there, almost done. So the Big Bang, is the idea that everything came from one place, it all exploded, and the universe is still expanding. They largely say that this is true because of the fact that Mr. Hubble and his telescopes found that things are still expanding. So if they're expanding, they must have come from a point where they weren't expanding. So they must have come from one point. That's what they're saying. All right, that's what the Big Bang is. They think it happened between 13.7 and 13.8 billion years ago, very long time. But not too long. If you think about how old the sun is, it's 4.6 billion years old. So it's not like, if you think about how long everything lasts and everything, it's not like it's super, super old. I guess it is super, super old, but let's see if I don't need you guys to know anything here. This is just sort of how they believe everything works. So, after the explosion, those tiny particles mixed with light and energy, and then they formed atoms like hydrogen atoms and helium atoms, and those hydrogen and helium atoms formed stars, and then they formed planets and galaxies. Their stars eventually blew up, making black holes. And there's tons of things like asteroids and comets and stuff like that. Oh, it says it right there. It took a very, very long time. Take me home, country roads. What the heck, Chloe? All right, and then our future. There's 3 different futures that they think could happen as far as the universe goes. There's one where our universe just keeps expanding forever. Just keeps getting bigger and bigger and bigger. Things get further and further apart, which means that it'd be further and further apart from all our galaxies from one to another. Another is that eventually it'll just stop expanding and just stay steady. And then the third is where it expands for a long time and then it does the opposite and it's cooling down, and then what they call the big crunch happens where we go back to a single point and it goes. That's the three different things that happen. Honestly, I think this quiz is only going to be 5 questions long. Because a lot of the stuff you guys don't absolutely need to know. Anything else I need to know? Another cool thing is that, like, using, gravity calculations, they figured out that, not all of the visible things account for all the matter in the universe. And there has to be something else, which they call dark matter, is like matter that we can't see that's out there, or else gravity doesn't even make sense, which is sort of cool. So there's stuff that we don't even know about yet. A lot of stuff we don't know about yet. I still think it's pretty cool. I'm going to stop recording now. I think that's it, right? Yeah. I still think it's really cool that, like, humans as a species know so much that we do. Like, there's so much we don't know, but if you think about, like, how we're just sort of like monkeys or apes, not monkeys, apes, like, how much we actually know about everything is pretty cool. Like, we know a lot of stuff. I think more than, like, personally, I don't really think that there's a lot of intelligent life out there, and for us being, like, one of probably the only intelligent life, like, for us to know as much as we do is, like, really, really cool. I think it's so cool that we're really smart. And just wait till we, like, become one with computers, then we're gonna know everything. It's gonna happen. A couple ways. We're a tiny big. Did I stop recording? I didn't.